Hello everyone, my name is Megan and I'm here with my partners Omar and Gabby. In this video we will be talking about systems engineering and what system engineering is.
Hello everyone, my name is Omar Barkawi. The International Council on Systems Engineering, which is a group that promotes international collaboration in systems engineering practice, education, and research, defines systems engineering as an interdisciplinary approach and means to enable the realization of successful systems. So, the systems engineer is in the middle of the development of a system. So, what the systems engineer does is take information from a customer who has needs, and this customer could be anyone from an old person to a young middle school student like yourselves. And the system engineer then interacts and specifies those needs to a development team who create systems or some kind of a working product that meets the needs of the customer. And in this process, the systems engineer also supports a life cycle process, which we'll go into further detail later. And eventually this results in a system, a working system that helps a customer achieve their need. And this system also interacts with the environment. So obviously this picture to the left has a lot of arrows and it might be a little confusing right now, but we're going to go into a little more detail and kind of show you exactly what systems engineers do through the example of a toaster. So in order for everyone to understand what systems engineering is and what systems engineers do, it's important to understand what a system is. So, what is a system? A system is a collection of different elements that together produce results not obtainable by the elements alone. So, then what is an element? An element can be a lot of things. For example, a screw could be an element, a ball could be an element, and these items on their own don't actually do anything. So a screw could be part of a larger assembly or system, but the screw itself on its own, being completely independent, doesn't actually function as anything. It's just a piece of metal that has a screw-like shape. A ball as well, for example a tennis ball, doesn't really do anything on its own, but it could be part of a larger system. So a screw along with a screwdriver and a person could be considered a system. This is a working system where the three different elements are working together to produce some sort of an action or end result, which would be putting in a screw, using a screwdriver into some sort of a fixture or something like that. Same thing with the tennis ball. Tennis ball on its own doesn't do anything, but once you include two people, two rackets, and the tennis ball, you can have a system, which is the game of tennis. So we're going to look at an example of a toaster, which has several elements in it. Three of them are shown on this slide. So one element could be just the power cord. Power cord on its own doesn't really do anything, but when it's connected to a toaster, you can make that bread brown, which is nice and toasty, which everyone likes. So same thing with the knob. The knob doesn't really do anything on its own, but when connected to the system, you can change the temperature inside the toaster and therefore change how you get your end result, which is your toast. And last on the right are the heating elements that are inside the toaster, which are controlled by the knob and several other factors, and they provide heating. But if they're not connected to an electrical outlet, they don't work, and if the knob can't change their temperature rating, they also don't work. Now that we kind of understand what a system is and what systems engineering is kind of about, and what the role of the systems engineer is, let's get into how a systems engineer actually accomplishes his or her tasks. So let's say one day you're eating some bread And the way you toast it is using a blowtorch, and you have to get gas to fill up your torch, and then you torch the bread, and sometimes you burn it, so you have to throw that bread away. But sometimes you get it right and it's perfect, and you don't like your bread soft, you like it toasted, so use this blowtorch. And then you get an idea. What if I had a machine that could toast my bread to my liking in an easy way? So what a systems engineer would do is go through the system life cycle to design, produce, and operate your idea, which in this case would be a toaster. So we're going to take you through the system life cycle over the next few slides. But there are three main portions of the life cycle. The first one is concept development, and this includes the needs analysis, concept exploration, and concept definition. In this phase, you're kind of looking at what your end product wants to do for the customer or for yourself, and kind of defining what it's meant to do. In the engineering development phase, which comes after concept development, you're getting into the full-fledged design, and then you're going to test it as well and perform a risk assessment before beginning to integrate and evaluate each one of these components that are within your toaster or your product. And lastly is the post-development stage. So after everything is designed and tested and seems like things are working, you get into production. So if you're a company building toasters, you want to be able to produce these toasters in an efficient manner, and this is kind of where you do that portion of your development in the system lifecycle. And this also includes operations and support. So let's say one of your customers has an issue with their toaster. How do you help them to make sure that they have a good experience with the toaster that they bought from you, so that they can continue being your customer and they can continue buying your brand of toasters? And again, we're going to take you through the entire life cycle with the example of a toaster. The first phase in the system life cycle is the needs analysis. And this phase mostly consists of making sure that the idea you have is an actual need for people and that it'll actually work out in the end. So first, you need to show clearly and convincingly that a valid operational need exists for a new system or a major upgrade to an existing system. So going back to the use of a blowtorch, a toaster could be considered an upgrade to this system. But the point of the needs analysis phase is to show that it's actually worth pursuing. So if you can see that this toaster is safer than using a blowtorch, it uses less energy, it's cheaper, and it works better overall to toast your bread, then that would be considered a valid reason to pursue this project. You also need to be able to present at least one conceptual system, something that represents your end product, so that you kind of show that it's feasible, it's actually possible to do this, it's not some imagination. It has to have sound engineering behind it, or at least the feasibility behind it, so that people can see that this is worth pursuing. And it also has to be developed and approved at an acceptable cost. Unless you have millions and millions and millions of dollars to invest in something, which most people don't, you have to consider cost as one of the big areas in starting a project. So lastly, you have to convince the stakeholders in this product to pursue the development of the system. And so stakeholders can be a lot of different people. For one is a customer. Two would be someone who's investing. So if you're a company and you want to create a toaster, you're going to need money from somewhere. So unless you have money stored away in which case you would be the investor and you'd have to convince yourself to pursue it. You'd have to convince other investors that it's worth their money and time to produce this product and develop. After you've convinced your stakeholders to invest and pursue the project that you proposed back in the needs analysis phase, then you can move on to the concept exploration phase. And this is where you convert the operationally oriented view of the system that you looked at in the needs analysis phase into an engineering oriented view of the system. So that means starting to create requirements that are more technical and kind of like narrowing down what kind of a system you want to pursue. So you need to provide explicit and quantifiable basis for selecting an acceptable functional and physical system concept. This basis is what you're going to be using in the future to make sure that you stay on track and you meet the requirements that you set here and then maybe in the next couple of phases that are a little more narrowed down. And then you want to come up with some candidate system concepts. So depending on what you set as your requirements, you can have a whole different kind of toaster. So the needs analysis phase, you pretty much said, I need to toast some bread because I like toasted bread. Now you're looking at, in the concept exploration phase, you're looking at maybe what kind of bread do I want to have toasted. If it's just the standard square-sized toast, then you can have either the system concept on the left or the one on the right, because those take the square size. But if you're looking for a more rounded loaf that you plan on toasting, maybe you go for something in the middle, shown on the slide, where there's a chamber that holds toast that is that size. If you wanted to toast hundreds of toasts, then go with the system on the right, because that can obviously take many pieces of toast. So in this phase, you're pretty much kind of setting the standard for where you want to go, where you want to direct the project, and then from then you're going to narrow it down in the next few phases. Now that you have some system concepts to work with, you can narrow down your concepts in this concept definition phase, which is the third phase of the life cycle and the last phase of the concept development total phase. So this is the third and final phase of the concept development phase. So now you're getting into a serious, dedicated effort to define the functional and physical characteristics of the new system that meets the proposed requirements in the previous stages. So you set some requirements in the last two stages, and you need to meet those requirements unless they've changed, which is possible because the systems engineering life cycle is very iterative. So you can go kind of in circles a little bit until you narrow down and you get that final concept that you want to pursue. But also in this phase, you need to start characterizing the operational performance. So when the product is done, what is it going to do exactly? And you need to be able to quantify that and say, this toaster will take 2 pieces of toast that is this thick and can go in this chamber, and the heating element can go to this temperature and therefore produce this final end result of a toasted piece of bread. You need to start quantifying this in a good way that makes sense. And you also need to start characterizing the time of development. So the toaster, you might have a competitor making another toaster, so you gotta maybe beat that schedule that your competitor has. You can't take forever to make this toaster, otherwise you're just never going to see an end product. So you have to start setting a schedule that you can meet realistically after designing in full detail what the toaster is going to look like and then start producing it. And you also have to start characterizing the life cycle costs in quantitative terms. How much is this toaster development actually going to take? What are the basic material costs? What do you have to pay engineers to develop this toaster? So all these things you have to start really narrowing down in the concept definition phase, as well as truly characterizing the end result.
This is Gabrielle, and I will be talking about the next 5 slides. The advanced development stage is for more analysis of the solution that was proposed in the concept definition phase. For a toaster, this might mean simulating the heating elements on a computer to see if they get hot enough. The engineering design phase is about the specifics of the parts, how they fit together, and making them into a working example of the product. A toaster would need a base, heating elements, knobs, and buttons, as well as electronics required to make it work. It also needs to be within the defined cost parameters and finished on time. Once one example of the product has been made, it needs to be tested to make sure it works like it is supposed to. A toaster might be tested to see if it can toast bread at different levels depending on the user input. Once the system has been confirmed as a success, a process needs to be defined to create many of them and to get them to the customers. For a toaster, an assembly line would probably be developed to mass produce them. Then they would be shipped to the stores to sell them. Systems need to be accounted for even after they are sold to customers. Sometimes parts break and the system needs to be maintained. These parts and the people responsible for maintaining the system need to be accounted for. This also applies to how updates would be managed if they are needed. A toaster is a relatively simple system, but it might still need available replacement parts. The simplicity also indicates that there would not be a need for continuous upgrades during the lifetime of the toaster.
Hello, my name is Megan Hyatt, and I will be doing the remaining slides. There are other parts in systems engineering as well, like the systems architecture. Many see a systems architecture as a communications tool. Architecture allows for parts, their connections, and constraints or limitations to be defined. By helping define the parts of a system in ways that everyone working on the project can understand, there will be less chance of parts made incorrectly or misunderstandings in the project. For example, the toaster, you might want to define the hardware and the software needed to run the toaster, but they may be defined in very different ways. Then how do we set up these architectures? After all, every project is different, right? And you might have different types of engineers or scientists or management on a project, and you have to define things in ways that they will all understand. So where do we start when it comes to drawing out and defining a system? That's where frameworks come in. A framework of an architecture is like the skeleton. It's a starting place for systems engineers. It's a way to express the architecture and allows for systems engineers to customize architectures to their project. Another large part of system engineering is dealing with risks. Examples of risks in system engineering are not being able to meet due dates or not being able to get the parts you need. Like if we were building a toaster and not able to get the heating elements in it, then it would never be able to toast bread, and the entire project would then be delayed or perhaps even canceled if we were never able to obtain those parts. Minimizing risks such as these are what system engineers do. When the development of a system begins, a system engineer must be able to see areas in the project where there might be problems. Then system engineers must try and prevent those problems from occurring. However, there will always still be some risk in a system. System engineers need to determine if the rewards are worth the risks as well. In this video, we covered a system lifecycle. The needs analysis, concept exploration, and concept definition are where your customer's needs are found, different solutions to their needs are thought of, and then one solution is chosen. The advanced development and engineering design is where any new technology is prototyped and tested and all the parts of the system are built. Integration and testing are where all the parts are put together and tested thoroughly, and operations and support are where the system is maintained. Having good communication throughout this whole process is really important. Sometimes customers don't really know what they want either, which makes it a bit harder. Sometimes the customer of a system will not be the user of the system. For example, if your parents bought and used the toaster, then your parents are both the customer and the user. However, if you use the toaster and your parents only bought the toaster, then your parents are the customers and you are the user. So system engineers have to help figure out what exactly the customer needs and wants, and also what the users need and want. Then a systems engineer has to make sure those needs are correctly translated into an engineering design. Other things we covered were the INCOSE, or International Council on Systems Engineering, an organization that allows for international collaboration. It's a great source of information about systems engineering, and we would encourage you to check it out. We also talked about system architecture, or how a system is defined, as well as some of the risks that occur in systems engineering. System engineers have a lot of responsibility, but because we have system engineers, it ensures that things are designed, built, and thrown away correctly. System engineering is also a lot of fun because you can see how many different systems are designed and built. Thank you for listening to our presentation.